we want to make sure we have a complete explanation for why these observations are the way they are. So what's the term in science for an explanation that explains why something is observed? Yeah, it's a theory or a hypothesis. Right? So if I'm just observing what's happening, that expressed mathematically is usually called a law. If I'm explaining why it's happening by coming up with some idea about how something's behaving that I can't really directly see or observe, like I can't really see the individual particles of the gas moving around, but I have an idea about how they're moving around, that's a hypothesis or a theory. And since gases have been so well studied in so many different experiments, we have a theory that explains how the gases are behaving, that explains these observations. Right? So those models, those simulations we just looked at, are based on the kinetic molecular theory. Right? So the kinetic molecular theory says a few things. I'm not going to go through these one by one, except to explain why these specific tenets of the kinetic molecular theory explain the observations, the actual observations we make about gas. Right? So the first one says that a gas is composed of particles that are separated by large distances. So how do we know that? Which actual observation about gas behavior suggests that part of the kinetic molecular theory is correct? We can't see the gas particles separated by large distances. So how do we know that that's true? What actual observation suggests that that's true? Yeah, the gases are compressible. Right? That's the difference between gases versus liquids and solids. Liquids and solids aren't really compressible. Gases there's a lot of space between the individual particles. So if I have a gas in a container, I can compress that container down. I just push the gas molecules closer together. I just get rid of some of that empty space. It's not difficult to do. Is there another one on here that also suggests that? Yeah, the fact that densities of gases are so low also suggests that. Because with the low density, that means there's only a small amount of mass in a given volume. If there's only a small amount of mass, you would expect that the particles that are creating that mass are not all packed close together, but that they have a lot of empty space between them. So if you shrank yourself down to the size of a molecule, and you were in a sample of gas, you might be in this room with a couple other people, but they would be strangers to you and you wouldn't have any attraction to them. Okay? So that's kind of how you want to think about how much space there is between gases. So the second part is gas molecules are in constant random motion. So we saw that in the simulation. That's part of the kinetic molecular theory. But what actual observation suggests that that's true? Yeah, the simulations we saw is based on the theory, which says that the particles of gas, the individual particles, are in constant motion. When they collide with something, depending on the angle of the collision, they bounce off in some random direction. But how do we know that? What actual observation of gas behavior suggests that that's true? Yeah, right, number one. Right, because the gas assumes the entire shape of a container in the entire volume of a container, that suggests that the particles that make up that gas have the freedom to move and continue in a straight line until they collide with something, and then eventually all those individual particles moving in straight lines and then colliding and changing their direction causes the sample to adopt the entire space of whatever container the sample is in. Also, number 4. If I put two samples of gas together, if I have one sample already present and I pump in another sample on top, it doesn't just sit on top. I don't get two different layers of gases. I get a homogeneous mixture because the gases are mixing together. That mixing is driven by the fact that the individual particles have motion. And they just keep moving in straight lines until they collide, until eventually all that random motion creates a thoroughly mixed container of the gas particles. So it's good evidence to support that aspect of the theory as well. Number 3, the gases do not exert attractive or repulsive forces on one another. That's a really important one, because that is definitely not something you can see. And we can't see whether the individual particles are attracting each other or not when we have a sample of a gas. So how do we know that that's true? What parts of an actual observation of a gas suggest that that's true? 4. Absolutely. Definitely. Very good. So in number 4, the fact that they're forming homogeneous mixtures definitely suggests that's true. If some of the gas particles could attract one another, then I would have the possibility, when I have a mixture of 2 different gases, depending on what the identities of the gases are, maybe I put in a gas made of polar molecules and a gas made of nonpolar molecules. I would expect the polar molecules, because they have opposite partial charges on opposite ends, to attract one another, line up those charges, form some dipole-dipole attraction. And those molecules would stick together preferentially, and the nonpolar molecules might be excluded, and I would get 2 layers of 2 different gases. But I don't see that. So I know that even when the gases are polar, they're not able to form attractions with one another. So making homogeneous solutions from gases, regardless of the polarity of the gas, tells me that the gases are not attracting significantly. Any questions about that? There's also another one, explanation for that we'll see more as we talk more about the gas properties. So then the last one is the average kinetic energy of a sample is proportional to the absolute temperature. Okay, so this is what everyone missed on the quiz. The average kinetic energy is proportional to, or measured by, the temperature. Once I know the temperature, that's all I need to know to have the average kinetic energy of that sample of gas. And this is not just for gases, this is for any substance. If I have a solid versus a gas, if I have a solid at 300 Kelvin and a gas at 100 Kelvin, the solid has more kinetic energy than the gas. Okay, because the average kinetic energy is not just how fast they're moving. That's not, the speed is not the same as the kinetic energy. Kinetic energy includes speed, rotation, vibration. In a solid, the particles don't have speed, right? Because in a solid, the particles are packed close together. They're forming attractions with one another. They're not sliding past one another and flying around like they are in a gas. But in a solid, there's a lot of vibration for the particles. So all I need to know, it doesn't matter what the state of matter is. Any sample at any state of matter at a higher temperature than any other sample at a lower temperature, the higher temperature sample has a greater average kinetic energy. That's what we use to measure the average kinetic energy. It's an average because, as we saw in the simulation, some of the particles are always moving slower or have less vibration and others have more. The collisions allow the motion to be transferred from one particle to another. But if I want to know the average kinetic energy, the average motion, including translation, vibration, and rotation, all I need to know is the temperature. That tells me. And so those two are proportional. So this fact that the density depends on the temperature is an actual direct observation that verifies that aspect of the kinetic molecular theory. Right? So really that's what temperature is. But if you measure the temperature, what you're measuring is how hard are these particles colliding with the particles in the thermometer. That causes the mercury or alcohol in the thermometer to move faster. Right? If something's colliding with it, the particles start moving faster and they expand and go further up the thermometer. So I measure a higher temperature when the particles have more motion. That's what I'm measuring. And so if I increase the temperature of a gas and I increase the motion, they move around more, and that expands it. There's going to be less mass in a given amount of space because the mass is expanded to take up more space. And so because the temperature affects the density and the other properties of a gas that we'll see moving forward, allows us to make this claim and be quite confident about it. Any questions about kinetic molecular theory? Okay, so you should have a good mental picture about how gases are behaving, what temperature is, and you should be able to relate what's happening with the individual particles to the properties that you can directly observe for a gas, the compressibility, the density of a gas, the fact that gases mix homogeneously, etc. Okay, so this is what we already said. Gases are compressible because the gases are made of mostly empty space, so we compress that down. Right? So if there's a lot of empty space between the particles, I compress them into a smaller space. What happens if I press the particles so close that they basically can't get any closer because there's no space between them? Now I have a liquid. It's not a gas anymore. You can make a gas into a liquid without changing the temperature. All you have to do is press the particles closer together. If I press them close together and that slows them down enough, all particles can attract. Even if they're nonpolar, they can still form London force attractions. And so those attractions will hold together and it will become a liquid. That would depend on the temperature, yeah. So if you had, if you compress these down and you still have a high temperature and they're really vibrating a lot and moving around a lot in that small amount of space, if I lift this back up and they still have a lot of motion, that motion can be expressed as translational motion and they can then fly apart, especially if their attractions are only weak London forces and it's not really strong enough to keep them close to one another. If I do change the volume here, they'll be colliding more. It gives them more opportunities to attract. Right? So some of the tenets of the kinetic molecular theory go hand in hand. One of the tenets is that the particles don't attract one another. One of the reasons they don't attract one another is because there's mostly empty space between them. So if it's going to really be behaving like a real gas, like an ideal gas, there should be lots of space between the particles so that they don't attract. And if I change the conditions that the gas is under, it might not behave like a gas anymore. Like we said, if I make the particles really close together or maybe slow them down to a really low temperature where they're moving so slowly, even if there is space between them when they actually do meet up and they collide, if they're moving super slow, their attractions might start to hold them together. It might condense into a liquid even if there is lots of space between them. So we can use the kinetic molecular theory to relate to all the different properties of a gas and predict how a gas will behave. So if I do change the temperature, the gas particles start to move faster, they collide more often, they collide at greater speeds, and the pressure of a gas will increase as a result of those collisions, right? So the pressure is related to the number and strength of the collisions. The pressure is 0 if there's no gas. The temperature is 0 if there's no gas, because temperature measures the average kinetic energy of a sample. If there's no sample, there's no temperature. So if I put some gas in here, the pressure goes up. So really, ultimately, the pressure, whatever pressure gauge you have, the pressure that you're reading here is going to be the result of the tiny particles colliding with whatever the sensor is on that pressure gauge. Okay, so the more particles I have, the more collisions I have, the greater the pressure. The faster the collisions, if I increase the temperature, we'll also see the pressure go up. Pressure will increase because now not only do I have more collisions as a result of the faster moving particles, the collisions that occur on average are harder because the average speed of the particles is being increased at a higher temperature as well. Then what's going to happen if I change the volume here? Compress this in with this little guy. changing the volume is definitely going to increase the number of collisions. So that also causes a pressure increase, right? So when you think about pressure, think of it as the result of collisions occurring. And when I have a lot of molecules and they're moving fast, they're colliding often, they're colliding hard, and that creates, both of those aspects create a greater pressure. How does a temperature increase affect solids and liquids? Right here. How does the temperature increase affect solids and liquids? Yeah, it's the same thing as a gas, except in a solid, most of the type of motion is vibrational. So if I have a solid and I just increase its temperature, the particles vibrate more. If I then melt the solid, a lot of that motion, now that I put in during the melting process, will cause the molecules to have more translational motion, more rotational motion. They'll be able to slide past one another. But in a liquid, there's still some attractions between the particles. So they're not able to break all their attractions and completely separate from one another. They still stay close together, and they break attractions and then slide past one another and form new attractions. So then if I keep adding temperature, they keep moving faster, and then they start to speed up, and eventually if that speed breaks the attractions between the molecule and the neighboring molecule, then I get a gas. 11.5. Which of the following statements is correct? The first one is, heat is produced by the collisions of gas molecules against one another. Is that correct? No, that's completely not correct. Right? So the reason I mention that is because that's a lot of people think about heat as being friction, or if the temperature goes up, there's more friction. That's not the way you want to think about it for tiny particles. Okay? Or even for anything, really. If you have a higher temperature, it's because the particles are moving faster. So if I have slow-moving particles at a low temperature, how do I get them to move faster? Yeah, how do I get the temperature to actually go up for those particles? I'd probably put the particles on a hot plate, right? Or use a Bunsen burner. I have to expose the slow-moving particles to fast-moving particles if I want them to move faster. Right? There has to be some type of transfer of that kinetic energy. So if I've got like a barrier here, and I've got maybe my slow-moving particles that are just, randomly moving around slowly. If I want to speed their temperature up, they have to be collided with by faster moving particles. So I could put this on a hot plate where the particles on the hot plate are vibrating really fast. Right? The hot plate's at a high temperature because the surface molecules are vibrating a lot. Higher temperature, more motion. So when these particles that are moving slowly come down here and collide here, if they collide with the surface of the container that's touching the hot plate, that vibrational motion on the hot plate will cause collisions into the bottom of the container, which will start vibrating faster. And then when the slow-moving gas particles come in there, those vibrations will push them, and they'll start moving faster. So the way to transfer motion is through collisions. That's the only way you can increase the temperature of something. Other than light. I mean, you could use light energy to come in and make things start moving faster. So you can always convert one form of energy to another energy. But if you want to heat up a sample, generally you do that by using a hot substance that has particles moving fast and allowing those fast-moving particles to collide with the slow-moving particles. Those collisions will help the slow-moving particles move faster, and then you'll have achieved a higher temperature for your sample. So it's not correct to say that heat is produced by collision. The collision is the result of the fast-moving particles. So you can say heat is transferred from one substance to another substance through collisions, but it's not produced by the collisions or by friction. The second statement there says, when a gas is heated at a constant volume, the molecules collide with one another more often. Is that true? Constant volume, so the particles fly, the amount of space they have to fly around in is not changing. I increase their temperature, so they start moving faster on average. So yeah, they'll start colliding more often. We saw that in the simulation. So they collide more often and harder with more force when I increase the temperature, assuming that the volume is